we're going to talk about the most modern model of the atom that we currently have. And this is where we're going to connect where we've been talking about waves and light and electromagnetic radiation and how that actually connects into our current model of the atom. Now, when we start to look at this, okay, we're going to start to see that the laws that apparently govern the motion of subatomic particles appear to be very different than the laws of motion of macro particles. So what we think of as Newton's laws and the laws of physics had to change and adjust in order to be able to describe this very interesting behavior and motion of particles at the subatomic level. This meant a new branch of physics was developed, which is called quantum physics. We'll talk a little bit about exactly what a quanta is in our video today. Now, when we last were talking about light and waves, okay, the wave model was our best way to portray the properties of electromagnetic radiation. That light was a wave, so it had wavelength, frequency, amplitude, etc. Okay, and that electromagnetic waves traveled at a fixed speed, which is different from waves that pass through water or waves in the form of sound waves, because those can be altered in their speed. However, there were a few things about light that did not seem to match up well with the wave model of light. First of all was the fact that when any object is heated, it begins to glow. Interestingly, as you continue to heat the objects as they get hotter, the color of light that's radiated, okay, as they're starting to heat starts with red, then it gets orange, then it gets yellow, and then eventually we usually get to what's called white hot, which is all the different wavelengths. Okay, so there needs to be, so there is interesting because the color depends on temperature. Okay, and that was an interesting question. Why did they behave that way? There's nothing about the wave model of light that would say that as things are heated, they should glow in certain colors, and they should. Why do they glow right along the visible light spectrum? Secondly, there's an interesting phenomenon as well, okay, that are called flame tests. Now, I'm going to kind of show and narrate for you a little bit of a video from YouTube. Now, flame tests are what happened when compounds containing metal elements or gaseous elements, okay, receive additional energy. Now, for compounds, the energy will be in the form of heat or flame. And for gaseous elements, the additional energy will come in the form of electricity. Now, the interesting thing is when they do that, specific elements will actually glow a specific color in the flame. So let me show you what I mean by this. So we're going to jump to a YouTube video. Okay, now these are compounds. Each of them contain different metal elements. Now, when these
but when I've done poured the alcohol across all the salts, and when I light one, all the others kept.
Okay, so what you're seeing here is metallic elements. in a flame. Sorry, I'm going to turn this down a little bit. I can hear it, you can't. Now, what you see here, I'm going to pause it for a second. Each of these different colored flames that you're seeing is originally a compound containing a metal, the metallic element thing. And they are soaked in alcohol, and then the alcohol is ignited. Now, as they burn, you can see that you see different colors. Now, the color depends upon which metal element is present in the compound. This blue color here, that's just alcohol, plain alcohol burning. Okay, and then we're looking at some different elements here. This one here, the very, very bright red one, is the metal element strontium, a member of the alkali earth metal. Okay, this beautiful green one down here is copper from the transition metal family. Okay, this one down here, which I'll turn, is very purplish. That's potassium from the alkali metal family. Okay, we have, believe this one down here is calcium. And this is boron is in here. Okay, so I'll turn on. You can look at the different colors. Okay, so they have very distinctive colors. These are called flame tests because this is one way we can identify elements that are present in an unknown compound. So if we take a substance and we burn it, okay, if you take copper wire and you hold copper wire in a flame, the flame will turn green. Okay, if you have a strontium containing compound and you hold it in the flame will turn red. Okay, this is calcium here, the orange flame. Okay, so these fascinating phenomenon, but nobody knew exactly why. Okay, so another question that we have is, where do these colors come from? Why do the different elements burn in different colors? A man named Max Planck is a German scientist, and he theorized that there was a relationship because colors have a specific wavelength. If you look at your electromagnetic radiation diagram, you can see the colors of the rainbow, right? And you can see that they have a very specific wavelength that's associated with them. Okay? And if they have a wavelength, that means they have a frequency. And Planck said that there was a relationship between energy and frequency. So Planck believed that the glowing bodies glowed because as a certain amount of energy, okay, remember, temperature is a measurement of average kinetic energy. So as energy was added to the substances, okay, the more energy they had, the greater the frequency of the line. Okay, and if you look at the frequency scale on your electromagnetic radiation diagram, you'll notice that as you move from red to purple, the frequency increases. So as we add more and more energy, the color moves along from the red towards purple, okay, and eventually gives more of a white look to us. Okay, so Planck was actually able to calculate a mathematical relationship between energy and frequency, and this is called the energy equation. The letter E here, of course, stands for energy. Okay, this is the amount of energy, right, in a particular type of radiation. And the unit for energy is the joule, Joule, capital J for the abbreviation. This letter here should look kind of familiar. This is our little buddy nu, the Greek letter nu again. So that means that this stands for the frequency. Okay, which you'll remember is measured in hertz. Now, what is this? This is the constant that Planck had developed. Okay, that was necessary to show the relationship between energy and frequency. And it is called Planck's constant. Now, a constant means it stands for a just particular number that's always fixed. Planck's constant is 6.626 times 10 to the negative 34. So this means the amount of energy contained in radiation is equivalent to Planck's constant multiplied times its frequency. So let's look at a couple of quick examples of how to solve a problem involving this. Okay, I'm going to rewrite our equation here. Okay, so let's say, for example, we want to find out how much energy is found in ultraviolet light that has a frequency of 9.2 times 10 to the 16th hertz. Okay, so the E, energy, is what we're trying to find out. H is always 6.626 times 10 to the negative 34. And V, the frequency, is in hertz, so this is 9.2 times 10 to the 16th. Now I'm going to pull up my calculator here. Okay, and we're going to run that particular calculation. Okay, don't forget you're going to use the exponent button just like we've been working on. Alright, so 6.626 times 10 to the negative 34 multiplied by 9.2 to the 16th power, okay, is, and this calculator unfortunately doesn't give scientific notation terribly well. Okay, so I'm going to have to count. So I've got 1, 2, 3, 4, 5, 6. 17. Okay, so looks like about 6.1 times 10 to the negative 17. Okay, so that's how much energy we find in ultraviolet light. Okay, now, that's all well and interesting, but what does that really have to do with the structure of the atom? Well, Planck had an idea. Since only certain frequencies were given off, obviously, by atoms, so because if we look at those colors, a color is associated with a particular wavelength, which means one particular frequency. Planck believed that atoms could only absorb certain amounts of energy, and these are called quanta. And a quanta is a piece of energy. Now, this is a new idea when we think about energy. We tend to think about energy as something that just kind of flows, so it isn't actually particle-like. But now Planck said that energy actually had some particle-like properties. This is very different, and it represents a shift in the way we look at energy. Previously, Energy and matter were considered completely, totally separate and different, had different properties. Okay, now waves are not pieces. So how does this fit in with the wave model? Okay, well, Planck wasn't exactly sure, okay, but he was pretty conclusive that he could relate a specific amount of energy with a specific frequency. Okay, and he believed in these quanta, these pieces of energy. In other words, that energy had particle-like properties. Now, this is a little bit controversial. However, Planck's idea is going to become very, very important when we look at another interesting thing that atoms do. Now, if we look very carefully at those colors, we can pass them through what's called a diffraction grating. A diffraction grating will actually spread these wavelengths out so that we can see that the wavelengths are not actually one specific color. They're actually a blend of different colors. Okay, just like green light, you could say, well, green is usually a combination of yellow and blue. Okay, well, since green is actually in the spectrum, okay, but if we had a lot of wavelengths in one color, for example, a lot of red wavelengths, the light would look red, but there might also be some other colors. They're not very easy to see. Now, in order to see that this, we're going to be actually looking at gases. I think I just spelled receiving wrong. Nope. I spelled it right the first time. Sorry about that. Just looked wrong. Now, we're going to be looking at some gases receiving additional energy in the form of electricity. And you're actually going to watch this for yourself when you do your lab. Okay? So when gases get additional energy, they're going to go to the next higher state of matter, which is called plasma. Okay, so they're going to glow, and every gas glows a specific color, depending on what's the actual gas. Is it oxygen gas? Is it nitrogen gas? Is it hydrogen or helium or neon? Okay, so just like when the metal salts receive energy in the form of heat, they burn with a specific color. Gases, when they receive extra energy in the form of electricity, also glow a specific color. Now, we're going to pass what's called a diffraction grating in front of the gases. Now, diffraction grating is going to break the light up, just like a prism does, or water does when light passes through it after rain, and you see the rainbow. Okay, so we're going to look at, and this is called, the colors that you're going to see, it's called the atomic emission spectra. Okay, now I'm going to jump over to another YouTube video. Okay, now when he's talking about spectral lines, this is the atomic emission spectra. Okay, so he's going to put a piece of plastic up, and the plastic works like a prism. Okay, now this is the element hydrogen. See, this is a tube of gas with hydrogen in it. Okay, and it's plugged into a power source, so it glows. And then over here, he's got the piece of plastic, and when he kind of tips it off to the side, okay, you can actually see this color is actually broken up into specific wavelengths. Now you see certain lines, say little lines of light here. This is called the emission spectra of the element hydrogen. Now watch when he does a different element. Okay, so you see the pattern. There's like purple, greeny, blue, and red. Okay, just a couple colors, so only a very few specific wavelengths. Now when you look at the element helium, okay, notice helium's slightly different color. Now look at the pattern. Very different pattern. Look, more lines. Different colors, different lines. Okay, helium and hydrogen don't have the same pattern. So atomic emission spectra are sometimes called fingerprints because every element has its own specific set. Now this is mercury. Okay, you've heard of mercury vapor lights. Okay, they use these a lot in streetlights. Different set of colors. Okay, now we're going to look at a couple of other gases. This is carbon dioxide. Okay, so this isn't just one kind of atom. There's carbon and oxygen atom. Okay, but again, the point is that there are different patterns for the different elements, these atomic emission spectra. Now, this is what we call an incandescent light bulb. Look at, you see all of the colors and they're all smeared together. This is like looking at the rainbow. So any object that's heated and is okay, and isn't, we're not talking about gas. And in that case, what we see here is all of the possible elements. Okay, all of the possible wavelengths, which looks white. Now, in order to do that, okay, now we're going to look at a still photograph. Okay, this is the same thing. This is the element hydrogen right here. Okay, here's the lovely red line. Okay, here's that blue line. Yeah, this one's flipped over from the one you saw. And way down here, there's some kind of purple lines. Okay, this is helium again. See, there's a red line, but notice it's in a different position. Okay, here's yellow. And here's some nice blue lines. This is the mercury spectrum again. Okay, so here's a couple of like orange, a couple of yellow together, some green, a tiny skinny blue one, and a purple one. Okay, 3 different elements, 3 completely different patterns. Okay, this is uranium. Okay, look at those. Okay, now uranium, look at almost every single color is represented, but it's not just a complete smear of every possible wavelength. Every line represents specific wavelengths. So let's go back to our atomic emission spectra. So what is atomic emission spectra? It's a specific set of wavelengths, which are the colored lines, okay, and they're given off by elements when they receive energy in the form of heat or electricity. So the energy goes in the form of heat or electricity, the atoms absorb it, and then they release it back out in the form of light. And no 2 elements have the same pattern. Okay, so the next big question we have is, why are all elements different, and where are the lines coming from? Now this comes from a nice gentleman by the name of Niels Bohr, came up with an explanation. Okay, Bohr put Planck's theory kind of in with this observation of atomic emission spectrum, and he looked at the element hydrogen. Bohr said the following. Okay, here's hydrogen and here's the proton, the nucleus. What Bohr said is that, okay, in its normal resting state, that means that's a gas without extra energy, the electron would orbit the proton. at a specific distance from the nucleus. Okay, so when energy is added in the form of heat or electricity, the electron absorbs a certain amount of the energy. When it does, the electron jumps to an orbit that is farther away from the nucleus. Okay, but this is unstable. It has too much energy, so it's going to release the energy, and because it wants to go back down to its lower state. And when it releases the energy, it doesn't release the energy back out in the form of heat or electricity. It changes it into the visible light that we see. Now the wavelength, for example, a red line, would come from a specific drop from energy level 5 down to 2. Bohr believed that there were 7 possible orbits, as he called them. Each of them was a very specific distance from the nucleus. He decided to call these orbits, if you will. He didn't call them orbits. He decided to call them energy levels. He compared them to the steps of a ladder. Okay, and here's the tricky thing, and here's where one of the first clues that the electrons were not going to behave like objects in the world around us. Since there were only specific wavelengths of light that came out, the electrons must go from one energy level to the next energy level, and they have to release that amount of energy to drop down. But they don't actually pass through the space in between. This is what we call teleportation, which seems like science fiction, but this is what electrons do all the time. So the electron would be down here in this first level, and Bohr decided to call the normal resting state, the non-excited state, the ground state. And this is where the electron is normally located. When the energy comes in, the electron jumps to one of the other energy levels. Which one does it jump to? It depends how much energy it actually absorbs. It has to join enough energy to go out to one of the energy levels. Then it drops back down and it releases the energy back out in the form of light. Okay, so this would be the red line, and this would be if it goes from 5 to 2. Bohr did some calculations using Planck's constant, because he was able to determine the wavelength, because we can measure wavelength of the atomic emission spectra. Then he calculated the frequency that went with that, and then he calculated the energy. So he was able to figure out that there were 7 possible energy levels. He figured out all the possible combinations and came up with 7. So he ended up with 7 energy levels. Okay? Now, when the electron jumps, he gave that a special name. That's called a quantum leap. You may have heard the term before. So this is a jump from one energy level to another. Quantum leaps are when you go from one place to another place without passing through the space in between. That's what's called a quantum leap. Okay, so this is a new model of hydrogen. Okay, so now we still have the nucleus, and now we have the electrons moving around, okay, in specific energy levels. So the electron is only allowed to be in a specific place. So Planck and Bohr said said that energy came in pieces. They're called quanta. Okay, well, Newton and Maxwell said that energy was a wave. So along came our friend Einstein, and Einstein said, why can't the two things exist at the same time? He believed in what's called the dual nature of light. Okay, that meant that he said that energy was both wave and particle. Okay, so he wanted us to picture, okay, rather than a wave traveling through space, Einstein said, think of it as particles moving along in a wave-like pattern. That's what Einstein believed that energy actually was. So these little particles of energy, okay, like a whole string, like a string of beads moving like a wave through space. Okay, so that's what Einstein said. Now, so again, lots of names, interesting people. A man named Louis de Broglie said, if energy has particle properties, then particles can have energy properties. What he said was that particles have wavelengths. So that means that electrons are also waves. Now, the electron wave doesn't look quite like this. Now, if the electrons are going around in an orbit around the nucleus, then de Broglie thought that this is what the electron would move like. Okay, so this is the electron. I'm sorry, it's not the world's greatest artist. Moving around and around the nucleus like a wave. Okay. Okay, building on that idea, a man named Heisenberg came up with the idea, okay, that, well, if we're trying to find out exactly where the electrons are, if we're trying to measure them, if they're really going around like waves, can we somehow identify where they are at a particular point in time? How does that work? If we got a particle moving around in a wave-like pattern, could we actually measure it somehow and find it? Heisenberg said actually it's going to become very difficult to do that. He used the idea of, imagine that you're in a pitch black room and you're trying to find a partially deflated helium balloon. So since it floats, okay, but not so great, it can be anywhere within the four walls. Could be up by the ceiling, could be down there by the floor. And since it's pitch black, you can't see it. So how do you find it? Well, okay, you would kind of go in there and bat your arms around until you've hit the balloon. And you'd say, oh, there it is. The problem, though, is that when you strike it, you moved it. So if it was moving, you've changed its speed, And since you now moved it in a different direction, other than you don't know where it went, okay, you don't know where its location is very well. So Heisenberg said that the act of measuring something is going to alter it in some way at the subatomic level. Remember, everything we're talking about operates only at the subatomic level. It's not something we see in our everyday world around us. Okay, so he said that if we have a whole bunch of wavelengths together, okay, like the electrons, okay, we can get something that sort of looks particle-like, but then we won't know its speed. Okay? If we know more about it, how fast it's going, then we won't know exactly where it is. So Heisenberg gave us what's called the uncertainty principle. Okay, again, a different analogy is like trying to find pool balls on a table, and all the pool balls are invisible. You can see your cue ball, but you can't see the pool balls. Now you have to find the pool balls by striking them with a cue ball. You can see the behavior of the cue ball. So if the cue ball strikes an invisible pool ball, its direction and its speed will change. Okay. But that doesn't mean you can exactly find the pool ball, because when you hit them with a cue ball, they're going to move. And if they were moving before, you don't know exactly how fast they're moving now. And you're not exactly sure where their location is either, because you struck them, you say, ah, they were there, but where they are now, I don't know. Okay? And we can do the same thing with electrons by hitting them with photons. The photons we can see. A photon is a light particle. So we can use our photons to hit the electrons. So we can see the photons change their path because we can see light and their speed. So we can have some idea about where the electrons are. So what it means is now we're no longer looking at certain measurements. Now we're looking at kind of probabilities. So the uncertainty principle basically says is that the more you know about the location of an electron, the less you know about its speed and direction. Okay. In physics, we use the term momentum. We're talking about object's speed, which is also related to its mass. Okay, in other words, we're no longer going to be able to, okay, we're going to need to describe the location using mathematical probability. Okay, so if we bombard an atom with enough photons, try to strike the electrons, we can gather some information about where we think the electrons probably are. It's like a data set. Okay, we're not going to get every possible bit of data, okay, not all possible data points, but we can use those data points to kind of describe where the electrons are in general. Okay. And a man named Ernst Schrödinger developed a set of mathematical functions to describe the location of electrons. Now, this is calculus. I'm not going to show you the math. You don't have to, okay, because it looks pretty complex. The wave equations are called. Okay, wave function equations. Okay, and in our next objective, we will talk a little bit more about what came out of these wave functions, these wave equations, okay, to tell us about the location of the electrons and how is that going to change from Bohr's model.